Howdy, welcome back to Multar Aviation. So in this Part 10 aviation weather video series, I'm going to be talking about the lapse rate and cloud formation. So hey, I'm Dr. Andy Moulter. I'm a flight instructor, a CFI IIMEI. I'm a former corporate pilot, and I'm a professor of aviation. And aviation weather is one of those videos that I teach, so you're getting a free college education right here on YouTube. So in this video, I'm going to be talking about lapse rate and cloud formation, but a lot of the topics that I'm talking about are things that we've kind of learned about in previous videos. So if you haven't seen those, make sure you watch those, and also make sure you subscribe. That way you get notified every time I come out with one of these videos. And the reason why it's important to watch all these videos, and I know aviation weather is one of the most boring topics out there, and I try to do my magic to make it as interesting as I can, but even I know that my videos are going to be pretty boring. So, uh, thank you for those of you that have been watching. But it is important because every single thing that we're learning is a piece of a puzzle, and you need to have all these pieces of the puzzle to understand aviation weather. All right, so clouds. Clouds, they're pretty and they do stuff. And so, really, all clouds are they're just visible aggregates of minute water droplets and or ice particles in the atmosphere above the Earth's surface. So, this cloud here is not a gas. It's not water vapor. Water vapor is a gas that's invisible. These are actually liquid water drops that are just really small right next to each other. And then fog, that is a cloud, but it just happens to be on the ground. All right, so there's different reasons why clouds form, and so there's the vertical motion effects of unsaturated air parcels that cause the clouds to form. And so as an air parcel rises into lower pressure air, that that air parcel is going to expand, and as the air expands, then heat is dissipated, and we call that the adiabatic process. And so as the air parcel rises in altitude, the temperature is going to decrease at the adiabatic lapse rate, which is the rate at which an air parcel cools as it's lifted. And the standard lapse rate is 2 degrees Celsius per 1,000 feet for an increase in altitude. And then as it descends, then the air parcel increases in temperature at a rate of 2 degrees Celsius per 1,000 feet. But this is the standard lapse rate. So this is just kind of like a generic scientific average of the temperature change. So really, we have the dry adiabatic lapse rate and the moist adiabatic lapse rate. And so the dry adiabatic lapse rate, it decreases at a rate of 3 degrees Celsius per 1,000 feet. So you can see here on the left side is the temperature and the right side is the dew point. And so this air parcel is 18 degrees, and as it goes up 1,000 feet, now it's 15 degrees. It lost 3 degrees Celsius. And then 12 degrees, 9 degrees, 6 degrees, 3 degrees. So the temperature is decreasing at a rate of 3 degrees Celsius per 1,000 feet. But the dry adiabatic lapse rate for dew point is half a degree. So here it is 3 degrees at the surface, and then 1,000 feet is 2.5 degrees. Another 1,000 feet, 2 degrees. So it's decreasing at a rate of half a degree. And you'll notice here that as the temperature cools down, the relative humidity here increases because as you know the the amount of moisture that the air can hold is dependent on the temperature. So the warmer the air, the more moisture it can hold. And so relative humidity, as I explained in one of my previous videos, is just the ratio, the proportion of, or the percentage, how much moisture is in the air versus how much the air could hold. And so the same amount of moisture exists as we're going up in altitude. It's just that the air can hold less in a gaseous form in terms of water vapor before it becomes a cloud. And so here we see the dry adiabatic lapse rate of 3 degrees Celsius per 1,000 feet for the temperature and half a degree for the dew point as we increase per 1,000 feet. But then at a certain point, as you see, the relative humidity keeps on increasing, and then we reach what's called the lifting condensation level, the LCL. So this is when the temperature dew point spread is 0 degrees, temperature and dew point equal each other, and we have 100% relative humidity. At that point, above the lifting condensation level, now we're going to have the moist adiabatic lapse rate. Now, the moist adiabatic lapse rate, depending on which book you read, it when we go up in altitude, the moist adiabatic lapse rate is a decrease of 1.2 to 3 degrees Celsius per 1,000 feet. So In this example here from the Aviation Weather Handbook, which I've got a link for in the description of this video, um, you'll see here that the lapse rate here is 2 degrees, for example. It could be 1.2 degrees, it could be 3 degrees. So that's just what it is. Now, I want you to notice that the temperature and dew point are decreasing at the same rate. So that's because the air is 100% saturated, 100% relative humidity, and so it's just going to remain the same rate for both temperature and dew point with the increase in altitude. Now, we had that air parcel that went all the way up. It was 100% saturated. Now that air parcel may want to descend. And so because it's 100% relative humidity in the cloud form, when it descends, remember, it'll start decreasing at the dry adiabatic lapse rate. And let me get you my laser pointer here. So as it's descending, it's going to decrease, or the temperature is going to increase at the dry adiabatic lapse rate of 3 degrees Celsius per 1,000 feet, and the dew point will increase at a rate of half a degree per 1,000 feet. And so at this 5,000 feet here, it was 100% saturated, but as the air temperature warms, remember the air can hold more moisture, and so the relative humidity will actually decrease because now there's less moisture. Or the moisture is the same, but now the air can hold more moisture, and so now any moisture will now become a water vapor as the temperature increases, and we just don't have any more clouds. So this descending air parcel and the lack of clouds is very apparent when you look at like a picture of the Earth. You'll have like a set of mountains, and on one side you'll have the windward side, in which it'll be nice, green, lush, and air will go up. You'll get upslope fog, lots of clouds, and you'll have lots of moisture in that air. But then as the air flows across the mountain peak, well, it was at 100% relative humidity. You can't go more than 100% relative humidity. So once the air starts to descend again, well, the temperature is going to increase, and so all that visible moisture will now go back and turn into a water vapor, a gas. And so now it's going to be drier air. And you'll see that the temperature increases. And now it's just all dry. And so on the leeward side of a mountain, that's where you're more likely to get like less arid conditions, possibly even deserts. So other ways that clouds can form is through frictional effects. So here on the left side we have this area of high pressure air, and so if you watch the previous videos, you know that air circulates in an area of high pressure by flowing downward, outward, and clockwise. And so if you ever been talking to a weather briefer, you call 1-800-WX brief, and they say, "Oh, high pressure is dominating the area." That means that there's going to be very few, if any, clouds in the area because, as we just said, as the air descends, it warms up and the relative humidity goes less than 100%, so the air is no longer saturated and we don't have any clouds. But then on the right side here, we have an area of low pressure, and the air circulates in an area of low pressure by flowing inward, upward, and counterclockwise. And so as it flows upward, it's going to eventually reach its lifting condensation level, reach 100% humidity, and we get our clouds. And then my recent videos, I talked about the different types of fronts. And so here we have a cold front that's coming in and it catches up to, warm air mass. And so it forces that moist, warm air aloft. And so we can also get clouds that way. Okay, so what's the difference between a cloud and fog? What are the moist and dry adiabatic lapse rates? Why is one side of a mountain more moist and than the other side? So if you can answer these, then good job watching this video. If not, go back and watch it. But and make sure to subscribe. That way you get notified every time I come out with one of these videos. All right, thanks for watching.